lot of cold and cough going on. Huh? Hello. एक को भी तो आप मेल गेट कर देना नोबडी Okay, why don't we quickly begin with a quick refresher of what we covered on day one? What were the main highlights? Not in detail, but the main highlights. Hmm. 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 Mm-hmm. Hmm. Synthetic data. Okay. What else?
And EDA. EDA.
EDA.
Outlier treatment.
Yes. Yeah, that's important one. So outliers, missing values. What else you've done?
Why I think if we are having symmetric distribution or one distribution, we can use outlier treatment. If data is skewed, we can use capping and clipping.
Flooring and capping, yeah.
Mm-hmm. Standardization, normalization. We convert it with the data into codes.
Okay.
Machine learning about 7 steps, find business objects, data collection and data preparation, model selection and training.
Yep.
Model evaluation, feedback and meeting.
Absolutely. Anything else, folks, you'd like to highlight? So we spoke about the 6-step process, and today we'll be deploying that as well. So let me see if I can show you an article very quickly, which talks about what are some of the main steps when you're building any AI/ML model, right? So let me see if I can dig up from over here. If not, then I'll share with you later on. Yeah. So this is the one. I mean, it's on LinkedIn, so I'll share the link with you on the Teams, and you can share with the rest of the people. So this is a typical workflow for any machine learning or like AI in general, how you want to start, right? So we want to first define what is the business objective or what is the problem that we're trying to solve. What will be like some sample examples of the business objective or the problems from your own areas, from your own domain? Any examples where AI can be used? Huh?
What end users will be able to analyze the data. That needs to be defined.
Right. So like, what is the main utility of the model that needs to be defined? Yeah. What else? Like, I mean, but how do you define the business objective, for example?
Example, car price.
Hmm.
If I am having data, data on cars, different
Hmm.
parts, price,
Hmm.
model, mileage, all these things.
Mm-hmm.
What should be the price of that car? So
Okay.
having data, I can
Yes. So it's as simple as, whatever will make your business create the impact, right? So it could be as simple as like, understand the sales drop drivers, what is causing the drop in the sales, or it could be, what is causing the customer churn, right? Or it could be how do we sell more of a product, right? So how do we sell more? Or it could be also how do we lower expenses, right? It could be any number of business use cases that you're looking at. So that's what basically you start with, which is, how are you defining your business objectives and what will be the value to the business. So if you do this thing, what is going to be the tangible benefit to the business? That's what we have to highlight as a very first step, right? So once you understand the business objective, then you go and collect your data and you gather your data, you understand the data quality, you understand the structure, you understand where exactly the data is residing, and then you basically get your data in. And once the data is in, so we are beginning at this stage. So we are saying we have already figured out what data is required and we're gonna start building the model. And that's where we are starting our ML lifecycle, right? So this, we will not spend too much time in this particular module. This will be covering in some other modules, or we've already covered in some extent in the previous modules, right? Then you clean, transform, engineer features. This is data pre-processing. We have already spoken about this earlier on. And then comes the part of model selection and training. So how do we select the model?
pass of in this case, we use logistic regression, and if our target is continuous variable, for example, car price, student marks, how much marks students can fail, what is the probability, that also we can use some probability. So student height and weight, all these things, house price. So in that case, we can use like linear regression.
Okay.
And based on the requirement, and if our logistic regression is not performing well, we can use uh, find this is the brief.
Okay. So yeah, so it will be basically based on the huh? Type of data, the complexity of the data, what is your label or the dependent variable, what is it like, which type of industry you're operating in, whether it's a heavily regulated or you can build your own model, all of those things will play a role there, right? So, but the model selection is a trial and error. This is not a fix. Almost everything over here is a trial and error, right? So you need to figure out what works for you. There is no one confirmed recipe which is going to work across the use cases. So you have to try and then see what really works for you. And then that's what you have to really go on. Then the fifth step is model evaluation. What is that one? Fifth step. Uh-huh. Uh-huh. Hmm.
Regression,
Yes.
slider regression. Then we can use a different kind of errors. So if error is less, the model is good. So mean squared error, mean absolute error, mean squared average absolute errors.
Hmm.
There.
Hmm.
R square, all these things we can use. And if it is logistic regression, like we are classifying something, in that case we can use accuracy, but this is not a good parameter. If data is normally distributed, then we can use accuracy, we can use, but we can use apart from that we can use precision, which is like it's more. Sorry, what is precision?
No, we'll discuss that. I think the metrics is, how do you
Precision
evaluate your model? Yeah.
precision then
Recall.
recall.
Yeah, all of those metrics. So what will decide what metrics you will use? How will you know what are the right metrics for us to be using?
For example, if I am working on any medical, I am developing any machine learning model, which is from which I used logistic regression, and that I used for some medicine thing or some medical field, healthcare field. So we know in healthcare field false negative is critical because if my model says some person doesn't have cancer, but if he or she is having cancer, that is a critical case. So in that case, we can use metrics called recall, not precision. So if, for example, I am using logistic regression to classify email is spam or ham, in that case, false positive is critical because false, I am classifying one mail as a uh, uh, what is that? Spam, not spam, spam. But that is actually not spam. So that is false positive. So in that case, we need to reduce the false positive case. In that case, we can more focus, we should more focus on precision. So,
Okay. Anybody else?
Important, then
Yes.
go for record score.
Okay, we'll discuss all of those. So the model evaluation is, or the metrics will be predominantly dependent on whether you are building a regression model or a classification model. If you're building a regression model, there are certain metrics that we'll be using, right? And we'll be talking about that. If you're building a classification model, then there's going to be another set of metrics, right? So, and regression can be built using many, many different techniques. Classification be done using many different techniques, right? But that's what the model evaluation is. And which sample of data we do the evaluation on? Evaluation, which data? Test. So training data is when you have trained your model. Once you've trained your model, then you use your test data for doing the prediction and then seeing how good you are in your prediction, right? So that's what it is. Then once you've done the evaluation and you assess it is good for your business, right? There's not going to be any perfect model which is going to have zero error or the best accuracy or highest precision, right? I mean, there's not going to be a perfect model. Even if you have a perfect model, there's something wrong with that, right? So cannot have a perfect model. So let's say your precision threshold was that I am comfortable with a model which is having a precision of 80%. Now your model gives you 85%, so you can go ahead and deploy that in the production. Don't worry about what is the precision, all of that we'll explain. But then you deploy that. So how do you deploy that? You deploy that in some sort of cloud, or you can even have it locally also if you're doing a local assessment, offline assessment. So if you're going to do the online assessment, then you need to host your model on some server out there where you are providing your input data and you're making the prediction, right? And then you're monitoring its performance. That's very important as well. No model is built for eternity. The model performance will degrade over a period of time. Why would the model performance degrade? New data or the data distribution itself is changing, right? The customer needs and wants are changing. The user behavior is changing, right? There's a drift in the the model performance by itself, for example, right? So mostly driven by your input variables, right? Or your input variables will remain the same, but no longer the user wants that, or the user behavior has changed, right? So it could be a multiple things which is causing the degradation in the model performance. So, and we have to monitor that actively, how the model is performing, and that's how you will ensure whether model needs to be retrained or build a new model. I think we were having a conversation with somebody while walking to the lunch that, I mean, there are many, many different ways. One thing is like you can try to fix your existing model if it is a costly affair for you to retrain the model. or you may want to rebuild another model, which will give you that sort of lift in your performance, right? So that's what like the overall flow is. Let me see if I can find the part two also. I think it's here somewhere. Maybe it shows. I need to log into the LinkedIn to really dig up. This is part one. There's a part two is also somewhere. And then we'll start talking about the metrics and what we're doing. I think it's the same one. Anyways, I'll try to do it later and then we'll discuss that, right? So now talking about the like the entire life cycle, we will step into now building our very first model, which is the linear regression model, right? What is a linear regression model? Anyone who has read this article can explain?
Shall I explain? On board?
Not on board, just to verbalize that, yeah.
I need road.
Then come. You really need the board. Just be short so that we can move on.
So, linear regression is a regression algorithm. So any regression algorithm says what is the average of this is the regression any this is the any regression uh, algorithm talks like what is the expected average of conditional y given x. X is our input variable or it is the feature and y is our target. Okay, for example, if we are predicting some car price based on some feature, that is car model, mileage, all these things. Those will be our x because this is the input feature. Based on what we predict the y, which is a car price. Okay, so this is the statistically says what is the linear regression. So it also linear regression models this line is beta 0 plus beta 1x. This is for simple linear regression. Linear regression is having two types. One is simple linear regression, another one is multiple linear regression. Simple linear regression is if we are having one feature or one independent variable, which is our x, and if we are having multiple x or multiple features, in that case we call it as a multiple linear regression. So this is a multiple. This is the simple linear regression equation, and always this will if we plot x and y, it will give us straight line. So that is why it is a linear. So if we graph it x, this is y x and this is y, and if we graph if we plot all the x, if we plot all the x and y like that, it will give almost a line. So that is why this is a linear regression. And another thing it does, not only predict the y and x based on x, it also finds the relationship between its coefficients with the target variable. Okay. For example, how my target variable will change based on the coefficients. So B0 and B1, these are coefficients. These are coefficients. So B1 is our coefficient. B0 we can say this is also a slope. So this is not slope. B1 is slope. B0 is y-intercept. But both are coefficients. Okay, and we can also say theta1, theta0. So now this is linear regression. Another thing is if we in machine learning, we can say h theta of x equal to theta 0 plus theta 1 of x1. So this is simple linear regression. When we develop this linear regression model and if we give some, if we get some results, always there will be some error. Okay, so there are few assumptions. for this linear regression. Okay, first assumption is there should not be any multicollinearity. For example, if I am having theta 2 x2, so I am having multiple features. So for car price, to get the car price, for example, I am having features called mileage and car model. So mileage and car model, if we calculate the correlation between them, there should not be any strong correlation between the features x1, x2, x3, how many features will be having. There should not be any correlation. That is the first assumption. Second assumption is why should be, this is our y because this is our prediction h theta of x. We can also say y. So y should be a linear function of x. Okay. So y should be linear function of x. What I told here, this is the same thing. So if we plot x and y, we'll always get a straight line. Not exactly, but it will be a kind of straight line. This is the second assumption. Third assumption is, I told whenever we create some model, linear regression model, and we predict something, our prediction will not be like exactly same as the actual value. So always there should be some error. And there, if we get all those errors, now there should not be any pattern between those errors. For example, if I am having for car price 100, okay, if I get error called like 2, and for car price 200, if I get error is 5, for car price 300, we get error is 6. There is a pattern because whenever I am increasing the car price, error also increasing. So this should not be there in case of linear regression. So in machine learning term, we say it is called a homoscedastic. Okay, so error should not be homoscedastic because there should not be any pattern. So if we error should be random, so there should not be any pattern. Now, yeah, all these things we should, these are the assumption of linear regression. That is why we call linear regression as a parametric model, because uh, to do the linear regression, to develop any linear regression model or choose the linear regression model, there should be some assumption, whatever I told, those assumptions should match. If those assumptions not matching, we cannot use the linear regression model. Okay, if there is a multicollinearity, if it is not straight line, if y is not uh, linear function of x, and if here, if it is not going in drawing the straight line, if we plot it, and if there is a pattern in the error, all these things, then we cannot use linear regression model. So this assumption should be satisfied before we go for linear regression. Now for linear regression, this is the basic of linear regression. And this also theta 0, theta 1, theta 2, all these are uh, coefficients. Okay, so this is the example of multiple linear regression, and simple linear regression. Instead of theta 2 x2, we'll stop here because we'll be having only one input variable, and another one is like this is the y is, there is no restriction, because y should be one only, but here input variable should be one. Another thing is for linear regression, this is not for linear regression. In any regression algorithm, output should be continuous value. Okay, so for car price, that is a continuous variable. It should not be like categorical. So if our target is continuous variable, means the value will be on certain range. For example, if this is our target variable, there should be any range A to B. Okay, so this is the continuous variable. So if our target variable is continuous, we can use linear regression. Another thing, okay, this is the basic things. Now we can calculate, we can theta 0, theta 1. So in linear regression, whenever we get the error, there should be any optimization process, okay, to reduce the error. Because when we develop any linear regression model mathematically, if we do mathematically in first step, we can see there are error is much. So we need to reduce the error. Okay, so to reduce the error, there are many optimization technique. First optimization technique is gradient descent. Okay, so using gradient descent, we can reduce the cost function. So for linear regression, this is the cost function j of I am telling about the simple linear regression. Theta 0, theta 1, 1 by 2m. I equal to 1 by m, and this is yi. So this is the error. Okay, this is the error means difference between the actual value what we have labeled already in our data, and this is the prediction. Prediction means what our machine learning model predicted. Okay, so this is the cost function. This is the mean squared error. Okay, this is a square. Okay, this is the mean squared error. So as a ML engineer, okay, we should reduce the error. So if error is very high, our model is not good. So there we should have some way to reduce this error. So way is there are multiple optimization technique. One optimization technique is called gradient descent. So in gradient descent, we can reduce this cost function by updating theta 0 and theta 1 for simple linear regression. So theta 0, theta 1, we need to continuously, iteratively, we need to update. Okay. So formula is for theta 0. If we want to update the theta 0, it is like theta 0 equal to, it is the new theta 0, theta 0 old. Okay, because this is the old theta 0 what we already have having, minus alpha. Alpha is the learning rate. Okay. Del of loss, del derivative of loss, delta L by delta theta 0 old. Okay, so this is called gradient. Okay, so we need to calculate this gradient. Based on that, we can update theta 0 and theta 0 and theta 1. There is a formula to update theta 0 and theta 1. That is all part of gradient descent. So if we see the code for linear regression, there is an option after creating the instance of linear regression. And after giving the training data, okay, we have one method called feed. So inside feed, all this happens. Like first, it will calculate, it will assume the value of theta 0, theta 1, some random value. Based on first iteration, it will get if predict some target, whatever we are targeting this value, h1, x1, y value. Then gradually it will update theta 0 and theta 1 to reduce the error. And when error is, this cost function is less, okay, we'll get theta 0 and theta 1 already. For that theta 0 and theta 1 for which cost function is less, based on that it will give the equation. For example, for theta 0, if for theta 0, 2 and theta 1 is 3. Just for example, I am getting a line where it goes through for which error is very less, because for example, like these are actual value, and from this line, distance from the actual value to this line is very less. So we can, if we can draw this kind of line, or for in simple term, for theta 0 to theta 1 3, error is very less. Okay, we'll get this kind of equation, h theta of theta of x equal to theta 0 2 plus theta 1 is 3 and x1. So this will be our linear regression equation. Okay. Now after getting this equation, x1 we already having from any new data. So for example, if I get any new data, so whatever value from data we get x1, we put this x1. And if we calculate 2 into for a new data, if x1 we get 6. So 6, 8, 2, 3, 80 plus 2, 20.
Okay,
so
I think Arpan, we can wrap it up. Thank you so much. He's a PhD scholar. Okay, so we'll do this. So just building on what Arpan was just talking about, we will fast track now and talk about some of the fundamentals. I mean, is this clear what you just heard from Arpan? Anybody has any questions? All good, folks?
A little bit about mean square error and the mean absolute.
Right, yeah. Because the reason I'm saying is one of the feedback we have heard is that people have been able to complete the module, but they're not able to do things hands-on or explain things hands-on. So I'll give you your first assignment in the class right now. And again, we'll follow a random number generator. I'll ask randomly one of you to come and explain everything we have done. Is that fair? So if something is not clear, feel free to stop. You never know if you are the lucky one to come and explain end to end. So that's how we're going to do it, right? So just make sure if it is not clear, raise your hand. And I'll just, for the benefit of the group, I'll at a very, very high level explain again. You can stop me if something is not clear, right? So as Arpan was explaining beautifully, so there are two broad categories of the models in any ML. So one is called the parametric. The other one is called the non-parametric, right? Non-parametric. So parametric meaning it assumes a certain relationship between the Y and the X's, a particular relation, right? A specific relation. So it could be a linear relation, it could be a logistic regression, it could be any other regression type. So there's a particular equation that needs to be formed. So linear regression is one of the method in the parametric module. There are other methods like a decision tree, right? Or random forest and all of those things. Those are non-parametric. They don't assume a particular relation, right? All this says that there is some sort of correlation between the variable, between your y and your x's, right? So they are some sort of function, right? Now, what do you mean by correlation? We spoke about this last time. What is the correlation?
How variables are related to each other. It's one variable increase, another variable will increase or decrease. So that is the correlation.
Okay. Let's begin the random number selection first. Linton, what is the correlation? You go with Linton or Anton? Linton. Linton, huh? What is the correlation? Hmm. Can you give some examples from the real world?
Of medicine,
Mhm.
the health of a person. So if you say that if you take the medicine, the health improves.
Hmm.
So that's a positive correlation.
Hmm.
And if that medicine is taken and if the health deteriorates, then it's a negative correlation.
Okay. Great. You want to talk about what is a linear versus a non-linear correlation? No? Let's pick another person then. Naveen is in the class? No? Online? Naveen? Vedant? No? Linear. What is a linear versus a non-linear correlation? Just from your own thoughts, like, what do you think might be a linear versus? Hmm. Hmm.
Another factor like that. So is whatever the person just he's able to able completely. That is what we call this as a linear. But I'm
Yeah.
not sure about the
Non-linear. Okay. Hmm. Yep. Yep. Absolutely. Changing what? Okay.
One variable is not an inconsistent variable.
Uh-huh.
It's like, say, consistently related.
Yeah. So I've drawn like different data points over here, right? So we can assume this is your X and this is your Y or feature or label, right? So now if you were to fit a curve fitting, everybody knows, right? So you just not doing anything, but you're just trying to fit a curve, right? So let's say I'm going to fit a curve over here. So the green line like will go something like this. If it is a perfect line, right? Similarly, the red will go like this and blue will go like this and yellow is like this. So let's say this is line 1, line 2, line 3, and line 4. Which one of these, or I mean the curves, not the lines, I'm already giving you the hint. Which of these curves are non-linear? Line 4 is a non-linear, right? So your linear regression will work for L1, for L2, for L3. It would not work for L4. Why? Because the linear regression says that I'm assuming my relationship is like this: beta 1 x1, beta 2 x2, beta 3 x3, and so on and so forth, right? Till the n number of variables. So it is saying why there is a linear, because there is a change in x1 by a certain amount, y changes by this amount, right? If I had x1 square, that's a nonlinear. Or if I had under root of x1, that's a nonlinear, right? Or if I have x1 cube, that's a nonlinear. Because I'm saying beta naught is nothing, y is nothing but beta naught times x1, beta 2 times x2. It's a linear relationship, right? So if you have like this, are these variables correlated or no? The yellow curve, are these variables correlated or no? They are correlated, but they're not linearly correlated. So that's the difference that you should understand. They are still correlated, but they're not linearly correlated. So it doesn't mean that this cannot be modeled. This can 100% be modeled, but probably not by a linear regression model. Why? Because linear regression model assumes that I'm going to follow a linear relationship between the y and the x. Is that differentiation clear?
Yes.
So this still can be modeled. Right. But maybe some other thing, non-linear basically. So it will be a non-linear curve that can be modeled by a non-linear method that we'll be discussing later on, right? But all of the remaining ones can be modeled by a linear regression. Is this clear? And similarly, the data point don't need to be always straight line. So for example, now I'm gonna use maybe if I can pick one more color. So let's say I have these data points, right? Like this, right? So line can still be drawn. It doesn't have to be going through point by point and all of that. So linear regression line is basically the line which reduces this error. Ordinary least square regression line is the line that reduces this error to the most. So it's not going to be 100% perfect line going through each data point, but it will be somewhere going in the data points too, so that the error is minimized. That's what the algorithm is trying to do underlying, right? And we'll be talking a bit more on this, but that's the main thing in terms of a linear regression. Anybody remembers the assumptions that Arpan was talking about for a linear regression? One is that y is a linear function of x. Linear function of x. Right? So that means y is beta naught x1, not beta naught x1 square or x cube or under root x1 or any other function, right? So that's the first assumption. Second assumption is that there is no multi-collinearity, no multi-collinearity, right? What do you mean by multi-collinearity? That x1 and x2 and x3 and x4, they are not related to each other. They are not linearly related to each other. So if you do the x1 and x2 distribution, so for example, this is the assumption. So if I look at the x1 and x2, the points should look like random, right? If I do x1 and x2 and they are doing like this, there is a problem in the assumption, right? So they should not be related to each other. They should be completely independent from each other. In ideal world, if they are completely independent, you will get a better regression model. If they're not completely independent, you will get some problems. And what is the problem? How does it surface? when you build a model, you're trying to estimate these coefficients by building a machine learning model. And we'll be looking at the equation as well in a minute when we do the California dataset. So what you're trying to do is your model is trying to estimate beta naught, beta 1, beta 2, beta 3. If you have multicollinearity, your coefficients are not accurate. So either the amount will be wrong or the sign will be wrong, right? So the sign will be counterintuitive. So when you assume that when I increase the, let's say when we increase the per capita GDP, the overall country's economy should be rising, right? Or the GDP of the overall country should be rising. But it says, no, if your per capita GDP is going down, I mean, going higher, your overall GDP is going down, which is counterintuitive. So you'll see coefficients which do not make sense. I really cannot understand what they're trying to tell, right? So that's a telltale sign that you have multicollinearity in your data set, right? So that's the second one. And the third one is,
Who are very closely related.
Hmm.
Don't consider them as a teacher because you can discard them.
Right, right.
So then the problem doesn't happen. Now, let's say if I'm evaluating some data where I don't know the domain.
Hmm.
So do I need to proceed with this kind of graph like X1 versus X2, X0 and X3?
Yeah. If you are forced by your business to build only a linear regression model, you have to go through all that activity. But if you had the option that you don't have to necessarily force fit a linear regression model, I can work with a decision tree, or I can work with a random forest, or I can work with a support vector machine, or I can work with any other algorithm for that matter. You will not overemphasize on force fitting your data in a linear regression, right? But only when your business says, no, you must have a linear regression model because of the, some regulatory or some legal requirement. That's where you have to do that, right? So let's say you do find out, to your question, let's say you do find out that X1 and X2 are related to each other, right? Now you can only pick one of them, right? So one of the things that you can do very basic is, let's try to understand what is the relationship of Y to X1 and Y to X2. Which one has a stronger relation? Let's say X2 has a R square you guys have done in your statistics. R square, coefficients of correlation. Huh? R2, R square. Anyone would like to remind R square?
How much variant model can extend? That is what that is that R square tells.
Right. So it's nothing but a linear coefficient of correlation. How much of X can be explained by Y or Y can be explained by X, right? So let's say R square in this case comes out to be 0.8 and R square in this case comes out to be 0.7. So X2 is a better predictor of Y. So then I will only have the X2 in the model, right? I will remove the X1 and not have it there. So that's the main thought behind that. And the third assumption, so we just spoke about, one is the linearity. So there's a linearity. The second assumption, who can remind me? No multicollinearity. No multicollinearity among X's. Right? So they should not be related to each other. They should be completely independent or to a large extent. And the third one is the errors are random. Errors are random, or they should have no pattern in the error. And I'll explain you why. No pattern, or they should be heteroscedastic, right? So errors should be random, or there should be no pattern, or they should be heteroscedastic, right? What does it mean, right? So let's say I build a model. So let's say I build a model to predict the house prices, right? So let's say I'm looking at my actual house price and I'm looking at my predicted house price, right? Now, let's say if I have a model which is behaving like this, sorry, not the predicted one. This is error. Error is nothing but your predicted minus actual, right? Now, let's say if I'm looking at a model which is behaving like this, where the error is showing a pattern. And you can imagine more data points are there. What is the problem with this model? So this is the actual house price. And this is your error in the prediction, which is nothing but your predicted minus actual value. What is the problem here? There is a pattern, right? Error has a pattern. What is a pattern? That as the house prices is going higher, what is happening with the error? Error is getting higher and higher, right? Now, this is not a very good model. So that means if I'm looking, let's say I'm just making up number, right? So let's say I'm looking at $50,000 mark over here, right? $50,000 house. So as long as your house price is less than $50,000, your error is low. But the moment the house prices start to go higher, your model performance is degrading big time, right? Because the error is getting bigger and bigger, right? Or error could not be just like distributed like this. Error could also be distributed like this, right? This is again a problem. That means your error is very low for lower priced houses and error is very low for higher priced houses, but error is high for the houses which are falling in the middle of the range, right? So these are what we call as your error is not following, your error is following a pattern, or they are not heteroscedastic, right? So if your error has a pattern, then this is not a good model, and you should not be getting into a linear regression model. Your error should be distributed like this, like a white noise. It should be homoscedastic, right? So there should not be any pattern, and it should be all randomly distributed. So no matter where I'm looking at in my prediction range, I don't find any pattern in the error. I'm equally good or equally bad. So it's not like on this range I'm good, on that range I'm bad, and in the middle I'm like doing best. So it should not be like that. I mean, none of those models will really work in the reality, right? So these are the broad three assumptions. So we have covered some of the fundamentals of the linear regression model.
So no pattern and heteroscedastic are kind of same.
Right. So this is homo, the pattern that I'm showing you right now. So it should be homoscedastic. Like, you can look up the word, but it's basically saying like, the pattern is similar. Homo meaning similar, right? Hetero meaning different. So there should not be a different pattern in the error distribution. They should be all the same pattern, right? So the three broad assumptions: linearity, no multicollinearity, and the errors are randomly distributed. So then you have a good model in your hand, right? Is this clear, people? So now we'll switch gears and we'll talk about how do we really evaluate the model as well. So I think I created something just now. I should save it in a different one, but that's okay. So whenever you're looking at the linear regression type of models, we'll be looking at the broad error families of errors, right? And by the normal intuition, error should be high or low? Error should be low, right? So error should be as low as possible. Ideally, error should be zero, but the moment you get to the zero, there is some problem in your model, right? So overfitting, or like, you have some sort of circular reference. Maybe your Y is also your X somewhere in some shape and form, right? So circular reference and all of those things. So error should not be zero, but trending towards the zero will be a better model, right? So let's say I built a model 1, model 2, model 3, and model 4, and the error is 0.31. I'm just making up something, right? And 0.49, 0.59, and 0.69. Which one is the best model? Model 1. Why? Because it has the lowest error, and that is the model you're going to choose, right? So it's as simple as that, right? But the $1,000,000 question is, okay, you just spoke about error, but how do we really define the error, right? So that's where some of these metrics are going to come in. So if you just pay attention on the screen, what we're doing is we're just generating some random numbers, right? And let's say we have generated these random numbers on the like the salary of the individuals, right? Or I don't know, I mean, what makes sense? 101, 142. Let's say these are your JEE scores based on the number of courses you've done in the past, your like CBSE score, whatever. I mean, basis on that, we are looking at your predicted JE score, 101 versus, sorry, your actual JE score versus what was it that model predicted. So let's say you registered for Allen or Akash or some other institution, and they say, I can give you what you want to score, right? And they have done a prediction on the JE score, right? So the predicted is the JE score and the actual is the actual that you've got in your, so there is an error, right? So over here, this student actually got 101, but the predicted value was 115. So what is the error? Yeah, so actual minus predicted is basically what your error is, right? So let's say I'm just making up like, some broad number over minus 14 is the error. What is the error over here, people? Minus 12, for example. What is the error over here? 64, 39, or let's say 40. So this will be 24, actual minus predicted, right? So if I just do this math, which is, minus 26 and 24, if I just add up all the errors and say on average, my error is how much? Let's just do the math. So tell me what will be the average error on this one? Minus 26 plus 24. So minus 2 divided by 3, which is going to be minus 0.67 will be my error. If I just take like all the errors and divide by the number of observations, right? But there's something wrong. What is wrong? Because it's not capturing the real errors that you're looking at, right? What is happening is that your signs are getting nullified, right? Because of minus and plus. So for example, if let's say very simply speaking, so house prices actual 40, predicted 50. Actual 50, predicted 40. So what is the error here? Minus 10. What is the error over here? Plus 10. So if I just take those errors, it will say I'm perfect model, right? There is no error at all because I've just taken the average error, right? That's wrong because you're missing the picture. So that's where we never add up the errors like this directly. So what can we do to fix that? Either we can take a square or we can take the absolute value. So just to take out the sign from the error, either we can take a square of the error or we can do the absolute value of the error, right? Just to really take out the sign and then we will be able to do the average. So that's the crux of the definition of the error. All the metrics. Now you can tell me what do you think this may mean? Mean absolute error. Who can define this? What will this mean? Mean absolute error, MAE.
It's first will calculate absolute means it will plus minus also it will be always plus and mean means average.
Exactly. So it will take the errors, take the absolute value of the errors, and then we'll take the average of those errors, right? Not just doing the average like this, because then you'll be getting 0. So what will be the mean absolute error over here? Who can tell me? Will be 10 plus 10 divided by 2, which will be 10, which matches with the actual error that we are looking at, right? So that's the concept of the mean absolute error. There is another one called mean square error. Anyone who can tell what this may mean? Yeah, so we take the errors, we do the square of the errors, and then we take the average of that. Then there's one more called root mean square error, RMSE. Any idea?
Root of it is mean square is right?
Exactly. So under root of the mean square error, right? Now, why do we have all of them? Any idea? Yeah, but why do we have many versions of the error metrics? Why do we have MAE? Yeah. So square will accentuate your error. Anything which is like, square. So when you do a square, so let's say the error was 10. When you do the square of the error, now the error becomes 100. Right?
What will penalizing?
Right. So more for penalizing the outliers in your data. So if you are making very wrong prediction on a certain data, if I do a square of that, I get better emphasis on how your model is performing on the edges, on the outliers, right? And whether it is doing a good job or not. So that's where the MSC comes in. Mean absolute error is, if your data is like, looking good, then you can use this also. There is another version called median absolute error as well. So mean and median, you guys are aware of that. So You can have either a mean or you can have a median, right? Similarly, we spoke about this, and root mean square error is just to really get it to the original unit of the error. So for example, if I'm doing a prediction of the sales price, so how do you really interpret the square of the sales price is slightly difficult for everybody. So that's where we take a root of that, and then it becomes also that you're paying emphasis to your outliers, and you're also getting under root. So your unit is preserved in that, right? Coming back to the same scale. Those are the concepts, right? So
Per unit, referring to each row of the data set.
Hmm?
The per unit of target.
Yeah. So imagine, like, I mean, when you're doing this prediction, so let's say your data has, your test data has
I have 6.
506 rows. Okay. So that means for each of the 506 rows, you're gonna get an error, actual minus predicted. And then this MAE is getting applicable on those 506 observations. Each row will be used to compute the MAE, right? And that's how you're gonna look into that data, right? So I'll give you like some time to read into it, just something we have discussed already, but happy to give you some time so that then I can assign your assignment to you, and then we will pick one person randomly to come and explain end to end. It's also, yeah, it's also driven by your business use cases as well. So like, how your, let's say, like, you measuring something in meter versus a feet, right? UK people will be measuring in, or us also will be measuring in meter, right? US will be measuring in feet. We'll be measuring our petrol in liters. They'll be measuring in gallons, right? They are the same thing, right? So if RMSE is going down, your MSC is going to go down and your MA is also going to go down. But which one is more comfortable with you depends on, what you have typically used for doing some of your modeling in the past, right? And what makes sense. But besides that, I mean, we also spoke about this, which is, good for interpretability. And this is less sensitive to the outliers, MAE. MSC is more sensitive for the outliers, right? Similarly, RMSC is like, the sensitive to outliers, but you want to bring it down to your actual unit on measurement, right? So that's what basically this is. And the last but the not least is the R square, which is talking about how much of the overall variation can be explained by your model. So I will come to it later on. I don't necessarily use R square because R square is a statistical way of building the model. These are a better way of building the model, which is the MAE, MSC, RMSC. Is that clear? All good? So on this data, you can see MA is 6.92, MSC is 90, RMSC is 9.49. So don't get worried about the difference in the scale because they have been defined in this way that MA is the mean absolute error, MSC is the mean square error and all of those things. So that's where the axis looks slightly different. Okay, so sorry, any other questions, thoughts? How do we understand the explainability? Like I said, I mean, so in this one, what does it mean? 6.92 mean absolute error, for example. Mean absolute error. What do you think that will mean?
Average of all the errors and refers to each data set.
Uh-huh.
And when you average it, and when you take mean and take the average.
Yes.
We'll come to know, and it should be less than 1.
Okay, so let's say for a data, I have a mean absolute error of 5. My predicted value was 25. Predicted value was 25. How do I bring in this mean absolute error? So on average, you are off from the actual value by 5 units. Because of your mean absolute error of 5, on average, you are off, your predicted values off from the actual value by 5 units. So what could be the actual value over here? The actual value could be either 20 or the actual value could be 30, right? So that's basically it's giving you the interpretation that on average, you're off by 5 units. It doesn't mean for every row you're going to be off by 5 units, right? So for some unit, for some row, maybe you're going to be off by 5 units. For other, you're going to be off by 10 units. For remaining, you may be off by 0. right? So on average, you're off by this. So it doesn't mean for every single prediction you'll be off by this. So it sort of like, helps you build the like confidence around your prediction, right? And we'll talk about a bit more on doing that. So that's what the mean absolute error interpretation is. Yes, 100%. So for like, when you're estimating something in this beta naught plus beta 1 x1 plus beta 2 x2, you have to make sure your x1 and x2 and x3 are all normalized. Have we spoken about the normalization last time? Yes or no?
Yes.
We have done that, right? Normalization or standardization, right? And that is there in my blog as well. So then you are bringing all of your x1 and x2 on the same scale. And that's where you can do a better job in the feature prediction. So that's very important that you do the normalization or the standardization to make sure we are good to go. Yeah. Okay, so this is a quick view of the error. And like I said, this is going to be applicable no matter what you're going to do down the road. So I think I have a better one that I can walk you through. Function exercise. Nope. Anyways, what you can do while I'm trying to dig up this link from my previous one, you can just go through this article one more time and try to familiarize yourself if something is not clear and let me know. Otherwise, you can start with your assignment while I'll do a walkthrough. You can just go through this and make sure that you're comfortable what we're doing, and then we can start this activity, right? While I dig up the right link.
entry for what we need.
This is the article number 28 on my blog. So I'll give you, I'll give you the assignment that you have to work on, but just make sure that you are able to follow through whatever is there. And if you have any questions, let me know. Okay, I will try to work on this code later on, but I'll just do a walkthrough very quickly for you over here so that you're clear, right? This is article number 28. So what we're doing step by step, and there are some examples where we can use a linear regression. We've already spoken about this. This is more in the mathematical notation, right? We have already spoken about the 6-step process, which is split your data into the features and the labels, right? Your, your DF will be broken into Y and X features and the labels, right? Then you take your X, screen is not shared. And then you take your X, you scale it, normalize it, right? So over here, you take your X's, which are there. You take it to the scaling and the normalization. So you'll basically get your X standardized or X normalized, right? And then once you've done your standardization, then you do your training and test split. So X will be broken into X train and X test, standardize, you can imagine. And then similarly, Y will be broken into the Y train and Y test. So far with me, everyone, right? And then moving down over here, then you will create your instance of the model. You come over here and you're creating your instance. So for example, the instance will be nothing but, let's say, linear regression, and that will be nothing but your linear regression. You have created that object, right? Then you're going to do the fit. How are you going to do the fit? We will do the LR dot fit on Y train and X train, right? And then we'll do the fitting, which is LR dot predict, and then we'll do the X test. So we'll get certain values. We'll call it as the Y predicted, right? And then in this last one, we'll be doing the eval, which is the MSC of the Y actual versus the Y predict, right? And then you'll get the mean square error and stuff like that. So that's the overall flow. Is everybody comfortable with this? So now let me just walk you through the code. So NumPy, Pandas, sklearn, some of these will be outdated. So just make sure that you are able to update the packages. Here.
So is actually we create the object, right? The linear regression. It finds the best line, right? The mean. So I just want to know, like, what are the iteration this actually object, not maybe not in the class, but I was just curious to know, like, what this guy actually has done with the data. So the data is coming to Y equal to, whatever C plus MX or whatever relation, right? So it is trying to go through the training data, whatever we are feeding the model, right? It's doing that calculation. And finally, we can find the coefficient and the intercept and make equation, right? So can we see that, like, how he's doing the program exactly?
Not in the sklearn, but you'll have to go in the it's all open source, right? So right. Yeah.
It's like 10 pages of calculation.
That's right. That's right.
If I have ID of this.
Yeah.
Yeah.
I know. I have seen the calculation. I'm just.
Yeah. Yeah.
Okay, fine.
Yeah. So in the sklearn module, I don't think there is any step like this. I mean, unless somebody has figured out, but I don't think there is a direct step for doing that. But I can tell you in principle what it does, right? So you have your X, you have your Y, for example, right? Or multiple lines. So it will say, let me see a certain combination of beta 1, X1. So it's trying to estimate, what is this line trying to estimate is these coefficients for you. These coefficients for you, right? And will be when we look into that Boston housing, you'll know what your X's are. So it's trying to figure out what is the correlation of, let's say, the neighborhood to the house price. What is the correlation to the distance from the highway to the house price, right? And all it is trying to do is, I mean, I'm just trying to explain you in a simple regression form. So let's say my data is like this, right? So shall I fit this line Or shall I fit this line? Or shall I fit this line? It's trying to fit like many different versions of the lines to figure out where the error is gonna be the lowest. So any type of modeling that you do, you have to specify a loss function, right? So what is it it's trying to minimize, or what is it it's trying to optimize for you? So in this case, it's trying to minimize the errors for you. And what is the error? Error is the difference between this line and the actual data points. So if I fit this yellow line, this is the error that we're looking at, right? If I fit this blue line, these are the errors that we're looking at, right? And so on and so forth. So it's saying, okay, if I look at all these errors and then follow the MSC, MAE, root mean square error, which of these lines is giving me the lowest error? And the line which gives me the lowest error is the best fitting line, right?
But this guy does immediately, right? The moment we create the instant of the object,
Right.
it does first.
For a small data, for a bigger data, it will take a while, right?
Thank you.
So that's all it is trying to do, but we'll go through the flow and we'll talk about some of the, how the engine works and all those things in a like future class. So NumPy pandas, all the usual suspects we've imported, magic command. This is the data set you will not be using, but I'm just importing this data set from the sklearn. I think it's now deprecated. You will not find it there. There's a, yeah, it's not there. So there is a California data set, but in this one, there are like, these are the variables like crime, zone, Indus, Chas, all of those things, nitric oxide, number of rooms. You can use from some other place. So these are what, any idea what are these? These are your features, X's, right? So when you're building a linear regression and then your Y is nothing but your house price. So you're building a model to predict the house price. So your model is saying, okay, I know your house price, HP, is a function of beta naught, which is nothing but like, if everything else is zero, then what is the house price, right? Which is a theoretical concept, but beta 1 times crime rate plus beta 2 times zone plus beta 3 times Indus and so on and so forth. You get the idea? Like, what are the X1, X2, X3? So those are all your features that you've given to your model.
So that is the question I was asking, like, that somebody looks at the data and you can tell that which of these particular will be highly correlated or can be used, other can be, discarded. Because
Sure.
when you do the calculation, you come know about one feature, right?
Yeah.
So, I mean, you told me about, I was saying that plot X versus X2.
Yeah.
So that is not relevant because looking at these data, somebody can easily tell that discard all this, just consider the crime attribute or consider the nitrogen oxide or some percentage in the air.
Yeah.
Maybe it's the pollution is more, people will not try to, price will be less.
That's right. That's right. So that's the bottom line. So anyways, we'll continue with the flow. Uh-huh.
So calculate the correlation. Only we should remove like strongly correlation things like someone defined it should not be more than 8. If it is more than 8, we remove that. If it is someone said it is correlation is more than 7, remove it. So how to decide like, what should we?
Yeah, those are all the statistical way of building the model, right? So what I propose for us to do is do not force fit a linear regression model, right? So let's say you say, okay, I know my data is not perfect. I know my data has multicollinearity. I know my data is having the homoscedasticity, I mean, heteroscedasticity in the errors as well. And it's not following the assumptions. Nevertheless, let me fit a model and see how's the error in the linear regression model, right? Then you'll fit the another model and then you get the error from there as well. Then you fit one more model and you'll get the error from there. You choose the best model because there's no point in artificially fitting a linear regression model, even though, I mean, there are like a lot of techniques. So for example, if you have the multicollinearity in your data, we'll be talking about something called as a principal component analysis, PCA, right? Which will take out any sort of multicollinearity, right? So we can fix them. We can then fit a linear regression model. But I'll say if you are not necessarily keen on a linear regression model, then we have many options that we can try out, right? I will explain. It's coming up next. So we're not there yet. So this is the data. So Boston description, it gives you a summary of, what these variables are, like the crime rate and all of that. And then it gives you these values. These are the house price values in the thousands of dollars, right? Now, this is where we are creating our data frame, right? How are we creating the data frame from the that bunch or that dictionary, Boston? We are getting the data, and then we are giving it the names of the features that we have. So that basically creates your data frame, and then we are appending the house price. So now you get your master data, which is your underlying features till here, and then this is your house price. Till now, we haven't done the features and label separation. So now we're going to move forward. Now we are running something called as a Boston df.core, right? And then we're doing the heat map and the correlation, and when we are doing a color mapping or the C map of red, yellow, green, and it basically creates this grid, right? I will pick a random person, see if they can help me understand what this grid might be doing. Sahawar? He's not there. Kartikin? You want to explain? I mean, I know I'm putting you on a spot, but it's on purpose only. What do you think this might be giving you? Just your own idea. You can do a research also, completely legal. Say, what does the df.core give? Do a fast research on Google and tell me. But you have to tell me.
Correlation between the data
Hmm.
and producing the heat maps.
And heat maps. But what type of correlation? What does it mean really? Yeah, but what do these numbers suggest? 1.49, 0.53. What do these numbers really mean? Hmm? Do a research, tell me. So you can say, what does this df.core or core gives statistical significance behind that? Anybody else can also jump in now. No, here there is no actual predictor. We're just looking at the correlation among all the variables. But my point is, what is this correlation telling me?
Is telling for each variable with the variable along or for example, one x means one variable and it is calculating correlation with all other variables and it is creating one matrix kind of things. And numbers are how strong or how they're how strong they are correlated. If it is like
The main idea is linear correlation. It's a linear correlation, right? So if you get this value as 0 somewhere, it doesn't mean that they're not correlated. They're not linearly correlated, right? So that's the main thing that you have to be looking at. So it's basically a significance of the linear correlation, and it can vary from -1 to +1. So if it is -1, they're perfectly negatively correlated. So one goes higher, the other goes down by the same amount, right? In a 100% negative correlation. So for example, what will be the equation looking like this? So you can be looking at -1 x1. If x1 goes up by 1 unit, y goes down by 1 unit. That's a negative perfect linear correlation. The other extreme is positive correlation. So instead of this coefficient being -1, this coefficient is now +1. So if x1 goes up by 1 unit, y goes up by 1 unit. So that's a perfect linear correlation. And how would it look in the picture? This 45-degree line is a perfect +1 correlation, right? Similarly, if I draw it right, this is a perfect perfect negative linear correlation. I hope this is clear. So now let's look into these numbers. I mean, I know this is slightly obscure to read. So house price to house price, what is the correlation? How do you read that? House price to house price. So you have to read like this and then look into this side, right? So house price to house price is 100% linearly correlated. which makes sense, right? So it's the same variable. What is the variable which is the strongest correlated to the house price? No, this is the same variable. So you will not take that variable in your modeling because it's the same thing, right? If you build a model, then you'll get the error 0. What is the other variable which is the strongest predictor of the house price then? L stat, right? Negatively 0.74. Negatively 0.74, right? And then what is the next important variable? This one. And this is again negative 0.51. Can anyone tell me what is L stat and P ratio? And again, you can do a Google quickly. For this variable, this data set, what is the L stat and PP ratio, whatever that variable is?
Lower status.
Lower strata population. L stat, lower strata population. And then, is it P ratio or PT ratio? PT ratio. What is PT ratio? People to teacher ratio. Now, can you explain whether these signs make sense? Linear regression, the thing that you have to always be watching out, do the signs make sense or not? Are we looking at the right thing or not, right? So it says, what does it say? So it says linear, I mean, not linear, it says lower strata to the house price is negative 0.74. What does it mean? Nope. Form the equation. The equation will be like this. House price is negative 0.74 times L stat. So as the, sorry, negatively, this is -7 minus, right? So as the proportion of lower strata population goes higher or more poor people live in that neighborhood, the house prices come down. Does that make sense, intuitively speaking? Of course, right? So as you are seeing more, like, I mean, if looking at Powai versus Navi Mumbai versus Dharavi, right? So in Mumbai, right? So which one has the highest number of lower strata population? Dharavi, right? So the house prices, I mean, I'm just making up, I don't know. I mean, not an expert in the real estate, so don't quote me literally on that. But my prediction will be the house prices will be lower in that neighborhood, right? Versus, some other neighborhood where the lower strata population is lower, right? Similarly, what will be the equation over here? House price is equal to minus 0.51 times people to teacher ratio. What is this one? Hmm. That's right. It's an indication. It's a proxy for the quality of the public schools, right? So if I have less pupil meaning you guys are pupils, right? I'm the teacher over here. So if I have less students for each teacher, that means teacher can give more attention. Imagine now 500 of you are sitting in this class. How much RP can do with the 500 people in that instance, right? Versus you guys being, selected group of people over here. So that's the thing. So if I have less student per teacher, that means the quality of the education is better. It's a proxy. This is not 100% like, one-to-one relationship, but it's a proxy. So it's exactly. So in the US, public education is free. Very few people go to private institutions, right? At least till 12th. Everybody goes to the public schools, right? I mean, unlike over here, we all go to the private school colleges. So there, most of the thing till 12th standard, till high school, as they call it, is completely free. But those schools, because of those quality of the schools, the house price will be very high. So for example, like, in Dallas, Fort Worth, I was living there for some time. Plano had the best quality of the schools, right? Versus some other neighborhood. So if you want to buy a house in Plano, you have to pay higher. Why people want to move there? Because education is better there, right? So that's the same thing that you are capturing over here. So if I have a higher people to teacher ratio, that means quality of the education is worse. The house prices will come down. Is that clear? So that's what basically this color schema tells you. Very, very important plot. But what is a big caveat over here? It will only work for, this map will only work for linear relationship, right? So if my relationship was like this, or was like this, or was like this, it will not be captured, right? Only it's capturing how much of one variable is linearly related to the other variable. And another big mother of all caveat, which is something that we discussed last time when I was talking about the Tom Cruise and all those movies, correlation doesn't mean causation. Just because two things are correlated, it doesn't mean that they are driving each other. They could be driven by a third factor as well. Remember the number of swimming pool death, chocolate consumption, all of those funny correlations we saw earlier in the last class. So correlation doesn't mean causation. You built a great model, but you cannot say with 100% certainty that this is the predictor for it. We are assuming this is a predictor, but there could be something else out there that is a predictor. These are just going in the weeds to sort of like, explain you what are some of these concepts. Now coming to your point, Linton. No, this is a multiple linear regression. Yeah. How to identify from this? So like the higher the coefficient, higher the linear correlation. So for example, this one, let's pick up this guy, DIS, distance. Distance has the smallest linear correlation, right? So if I were to plot my house price as a function of this, I think this is nothing but this is the distance from the highways, right? So it might be looking like this, something like this, a straight line, which looks like a very, very weak linear correlation, right? Versus if I were looking at L stat, then it might be slope of the line will be very strong, right? This coefficients are nothing but the slope. If the slope is 0, let's say beta 1 is 0, what does it mean? They're not linearly correlated at all, right? So that means if I am plotting something, let's say there was a variable and the slope is 0, that means line is like this. That means no matter what the x is, y doesn't change at all. So they have no correlation at all, right? They're completely independent. If the slope is 1, right? So that means a perfect positive correlation. If the line is like this, -1, then it's a perfect negative correlation, right? So those are the things. So this means that this is the weakest predictor, linear predictor of your house price as of now. Not in the US though. Again, like any model that you build, what works in India will not work in the US. People do not like to live next to the highways. They like to live in suburbs, right? Next to the highways, very like noisy, cannot sleep. Like some lunatic out there will remove the silencer of their vehicle and then driving at the full speed during the night, right? So all of those things are there. So it's not necessary that, I mean, you can say what, and again, that's like, your knowledge about that demographics, that particular landscape and all of that. So there it's saying, no, it's not, right? Okay, so shall we move on in terms of the flow? Then this is where we are doing the features and the labels separation. So from our data frame, we have just separated out X and Y. I hope everybody's clear. Features and the labels come out. Then we are doing the train test split, train X, test X, train Y, train all of this. And we are passing on two arrays, X and Y. And what is the test size? 25% of the data will be used for the test and 75% of the data will be used for training. Is that clear? All good? And you get the shape, which is 379, 127, 379, 127. So this is just for your information. This is nothing but who can tell me what is this array? This is X train. This is X test. Why is it X? Why is it X? Because you have 13 dimensions over here, right? So 13 features. So it says I have 379 rows and then I have 13 columns. So your entire X array is going on there. And this is the 75% portion. And this is the 25% portion. Is that clear? And this is your Y train. And this is your Y test. Why no dimensions over here? Because it's only one column, only the Y values, right? So that's all basically we're doing over here. So let's carry on down then. Then from over here, we are creating the instance of the model or the instantiation of the model. And we just importing the linear regression, calling it LM, right? Then we are fitting the model, lm.fit, train X, train Y. Then we are doing the prediction, which is the lm.predict on test. And then we are doing, some coefficients and all that I'll come to later on. But then I'm going to go follow the flow. What is going to be the flow? Which is now we're going to do the evaluation, right? So how are you doing the evaluation? np.round metrics.mean squared error, the actual values, the predicted values, then rounding it off, and the mean squared error is coming out to be 22. Similarly, we can do some other ones. I think we are doing some other ones. This is the mean. Okay, we are doing the mean squared, and then we are doing the mean absolute error as well. And again, you are importing the metric from there and then computing, right? And then we are doing many other things, like for example, over here, lm.coefficients. lm.coefficients is nothing but your beta naught, beta 1, beta 2, beta 3 for those things, right? Huh? Let me just finish and then we'll take a break. One of the things that we haven't done, can anybody remind me? We haven't done the standardization. So you have to do the standardization before doing that, because right now it's apple and orange comparison. So you really cannot take these coefficients on the face value. So you have to make sure you standardize your X before doing that. And then we are also doing the feature importance. After the standardization, your features will be much more on the same scale. And that's all basically it is, right? So on this note, you don't have to worry about this. On this note, we'll take a break. And once we come back from the break, I'll give you 1 hour before lunch. You have to finish this entire linear regression in the 30 to 40 minutes on a brand new data. And I'll ask one of you randomly to come and explain your project. Yeah. Is that fine?
Yes.
So we can take a break while I dig up the data that we have to do linear regression on.